Okay, class, we're talking about the ear, and the ear perceives sound. So let's get off on a discussion about sound first. Now, we had talked about the eye in an earlier video, and therefore, obviously, we were talking about light. Light can travel in a vacuum. If you recall, light had a duality theory. It was particulate with photons and also traveling waves. Sound has no particulate nature. There's no particle of sound. What sound basically is are vibrations. And sound travels much slower than light. As a matter of fact, uh, light travels at 186,000 miles per second, whereas sound would travel at about a 0.2 miles per second. So you see, that's a considerable difference, which brings me to the lightning and thunder effect. The lightning and thunder effect. When you see lightning, later you'll hear thunder. The thunder was associated with the lightning, but since lightning is a charge effect which can travel fast, and thunder is a sound effect, then the thunder comes much later. Okay? Now, when we get into this sound aspect, sound is a pressure disturbance, alternating areas of high and low pressure. So over here is the tuning fork. With the tuning fork, I'm going to hit this tuning fork, and what it will do is vibrate. So the air particles, the medium here, this is an elastic, you need an elastic medium. The air particles, the molecules of air, they will vibrate. When you hit it and the tuning fork moves in this direction, let's say, it would cause compression of the air. Then it bounces back real quick. So in other words, compression, rarefication. Compression of the air, rarefication of the air. Now what is that doing? And it's traveling in all directions away from here, but at a decremental amount. The further out you go, you're not going to get these vibration waves. Now, right here is the wave looking at in a sinusoidal S-shaped curve. Okay, this would be what's happening here. Now, what will happen is that we're now into this wave, and we're looking at three parameters, let's say, of the wave. Three parameters of the wave. One parameter is how fast the wave travels per unit time, and that's called the frequency. The other aspect is how long is the wave, and so I could go from trough to trough or peak to peak, and that would be the wavelength. The wavelength. And then the other aspect would be how tall are the waves, and that would be what we call the amplitude. So what do we have? We have wavelength, frequency, and amplitude. Now, the shorter the wavelength, the faster the frequency. Let me say it again. The shorter the wavelength, the faster the frequency that will occur. Okay? The frequency, let's go here. The frequency is measured in what we'll call cycles per second, also using the eponym hertz. Hertz. But cycles per second, and again, the shorter the wavelength, the faster the frequency. Okay? The frequency, when it comes to sound, is the pitch. The faster the frequency, the higher the pitch. The faster the frequency, the higher the pitch that you will hear. Okay? Now, when we're dealing with frequency and the human ear, here's what we're looking at. When we use the tuning fork, it's producing a pure sound because it's designed to do that. A pure frequency, pure sound. But when we hear something, it's a mixture of sounds. So let's say that you have a person, a soprano, singing high C on the music scale. And then, but there's a piano playing high C. Due to how our ears work, we have what we call the sound quality. And the sound quality is our ears are able to perceive high C separate from as far as the singer doing it versus the piano doing it. And that quality is what gives us the richness and complexity of sounds that we hear in music. Okay? So we go a little further here. Okay? So again, here's that frequency issue there. Now go to this one here. What is the hearing capability that we have? The hearing capability that we have here. And so here's frequency again, number of waves, wavelength we discussed. Just going back through it. The pitch, dealing with the frequency, quality we spoke of. Okay, so I go back here, hearing capability. And so what I did was put up a chart looking at the human, the dog, the cat, and the elephant. Now, our range as humans, remember hertz is a cycle per second, or wave per second, is about 20 to 20,000. That's our range of hearing. Dog, 50 hertz to about 45,000. So what does that mean? They can hear a higher pitch than we can. Remember, the faster the frequency, the higher the pitch. I go to the cat. Check that out. The cat can hear a higher frequency than the dog. And the elephant has a wide array. Look at that, 200,000. So they can really hear a very high pitch. Okay? But even though we can hear 20 hertz to 20,000 hertz, our best hearing range is 1,500 to 4,000, which is right in the middle. That's our best hearing range, 1,500 to 4,000 hertz. All right, we go a little further. So now we come to amplitude, which is the height of the crest, the amplitude. Okay, we'll go back to here. The amplitude, the height. Okay, and the amplitude is perceived as loudness. So the amplitude is how the loudness, how tall this wave would be, how much actual compression you're getting with this tuning fork. How much compression are you getting between compression and rarefication? Compression and rarefication. Okay. And so our normal range is about a 0 to 120 decibels. That's a measurement of sound. The decibel is a measurement of sound. And what the decibel system basically is, it's a logarithmic scale. And if you recall, a logarithmic scale compresses things because it's based on logarithms. It's based on the common logarithms. So with the decibel system, a sound of 10 decibels has 10 times more energy than one of 0, because we're dealing with the decibel system. Okay. But if you had a 0 decibel to let's say to a 10 decibel, okay, then that's 100 times more, but you was only heard as twice the loudness in your perception. So on the system, because it's logarithmic, then you're looking at multiples of 100, but in actuality, as far as your perception of everything, a 20 decibel sound would be twice as loud as a 10 decibel sound, to say it another way. All right, so I come here then, and what I did here was to look how loud is too loud. So leaves rustling, about a 20 decibel, 60 decibel normal conversation, busy city, hair dryer. Now, where pain is going to start to occur because you are, really bouncing around on that eardrum, where pain generally, most people will say about 120 decibels or above. Now, if you recall, the tensor tympani and the stapedius muscle tries to pull back on that malleus and stapes when the sound is too loud to try to prevent damage to the ear. But prolonged amount of 120 decibels or even 110 could cause ear damage. Government research suggests that the safe exposure limit is 85 decibels for 8 hours a day. Your hearing could be at risk damage if you are continually exposed to high volume sounds. Like here's that rock concert right there. Plane taking off and you too close. Gunshot and you too close and hear it. So that's what we're looking at when we get into that particular aspect. So now I'm going to do another video on transmission of sound to the internal ear.